structures. Graphene, well, the mobility is probably barely about million in the best case, so this is 30 times worse. Maybe we can say this slightly more correlated, and the correlation tend to be stronger because there is a less dielectric screening. It can be suspended or it can be put into the low dielectric screening environments. So you can promote correlations, but nevertheless, in the bottom line, we have not seen, or probably people have not seen yet, the new fractions, let's say. We are not aware of from the gallium arsenide to that. So that's the bottom line, but nevertheless, one intriguing and interesting aspect of this, looking at the quantum Hall effect, the fractional quantum Hall effect in graphene, is something that we have a bit of more controllability. I think that's something that I want to just stress throughout this the presentation, especially when you use a bilayer graphene. So let me just tell you about the stories. Okay, so these work, the presentation is large collaborations. The beginning part is most of the collaboration that I had at Columbia, and the later part, if time allows, I will go over some of the new development developed at Harvard. So we're just kind of composing the two pieces of the bit old story with a new story. So the graphene, we know that it's a hexagonal arrangement of the carbon atoms, and in the low energy scale, basically I can just kind of consider PZ orbitals for the tight binding. And simplest tight binding model already give pretty much good descriptions of what we need to understand the low energy physics. That's interesting. Important part is there are two bases in the unit cell, which means that usually Hamiltonian we describe it is better described by this the spinners, or often we call them pseudo spins, which can direct one lattice versus the other lattice. Not sure is if you just calculate the band structures in the low energy scale, basically the Fermi level is at the corner of the Brillouin zone, what we call the K or K prime point. But there are 6 points, but only 2 of them are inequivalent. So in a sense that I have the Valley degree of freedom in semiconductor language that I just kind of put the charges one Valley versus the other one. And each of the Valley, basically we have this nice linear dispersion relations. Moreover, it's chiral structures. In other words, the pseudo spin direction is tied with the momentums of the each valleys, and they're connected by the time reversal symmetry. So that's the basis of the single layer graphene. Of course, quite early on, this linear dispersion relations with the 2 Valley and K prime under the magnetic field, you can easily solve the problems. And interesting enough, under the magnetic field, by the way, especially as you go to the lower Landau level, the Valley index and the sublattice index is kind of equivalent, especially at the 0 Landau level. Basically, one wave function is sitting, one value of the wave function sitting in the one of sublattice, and the other one is just sitting in the other lattice. So as we go for the quantum Hall physics that we are going to discuss, basically the Valley index is more or less similar to the pseudo spin index that we are just dealing with in single layer. And that will play an important role later on. And quite early on that just after graphene's experimental discovery, it was clear that the sample quality is high enough under the magnetic field. They start to develop this beautiful quantum Hall effect, integer sequences of quantum Hall effect, which can be explained by basically the Barry phase shift of the half of this one of the filling fractions times of the 4 of the degeneracy factor for each Landau level, counting for the spin and the Valley spin or pseudo spin, same languages, right? So that was kind of simple things that we know about. Up to here, this is kind of completely single particle pictures. We don't consider any of the degeneracy breaking between the spin and pseudo spin. But of course now, since we have more or less internal degree of freedom, double the internal degree of freedom of the typical electron systems in the semiconductor, we have to think about what is this role of the internal degree of freedom. Even for the simple case, spin degree of freedom, if you just think about, dipole interaction of spins or Zeeman splitting is usually small energy scale, unless it's extremely large the magnetic field. So often in the first order approximation, we tend to ignore that and build up the idea. And that was in the previous slide. We can explain all this nice integer quantum sequence by just ignoring the spins, or as well as the Valley. But we know that once we just consider exchange interactions, in fact, the Coulomb interaction can be mediated by the spin arrangement to acquire relatively large energy if there is a kind of strong enough correlation. So that's basically interesting stories we can think about, how we can just combine this internal degree of freedom to come up with the interesting sequence, especially related with the correlation of the electron in the system. This story is not new. In fact, if you just look at the literatures of the gallium arsenide, already it has been realized it doesn't have to be even spin. The internal degree of freedom I can index it, or you can index the wave functions, can be utilized to create this kind of correlations by the exchange energies, minimizing this, maximizing exchange energies. Right? So it can be quantum or bilayer, or there's valley spins, and there has been a lot of studies already in semiconductor heterostructures utilizing some of the additional degree of freedom that we just can use. So the term of this multi-component quantum Hall effect is, in a sense, one of the essential part that relate with graphene physics, but also it is already has been studied quite heavily in the semiconductor physics. Quantum or Bilayer is a really good example, and a lot of exciting things comes out. The valley spin degeneracy that's controlled by the piezo is kind of recent work in the Shoyugen's group, and there are many examples you can find out. Try to utilize this type of internal degree of freedom. So what's new? Well, graphene, there is something kind of peculiar that when you consider this internal degree of freedom, unlike the semiconductor, often that you can create the nearly the degenerate internal degree of freedom of the spin by tuning the G factors, but often then you just can sacrifice another part or something. So having these two components of the nearly degenerate internal degree of freedom is a relatively new concept in semiconductor, the quantum Hall physics. Let's say in graphene, I would say that this internal degree of freedom is nearly degenerate in the sense that if I just carefully compute or evaluate this energy scale of each internal degree of freedom, it comes around. I think the most large energy scale is, of course, single particle cyclotron energies. Usually in typical magnetic field that I can access in the lab, that's the range of the hundreds of the millielectron. So huge, especially in the lowest lambda level. Part of the region is its linear dispersion relations. Now, if you just look at the Coulomb interactions, compared with the gallium arsenide sample, again, graphene that this dielectric constant can be controlled in principle even down to 1 if it is suspended. If you put into the boron nitride, which I'm going to discuss, that's about 4, so it's about probably 5 times better. So usually the correlation energy is relatively stronger compared with the gallium arsenide. Yet the Zeeman energies and then this sublattice scale of the atomic scale energies, which actually governing this the valley degeneracy, that's much smaller, probably about 1% or even less than compared with the other two energy scales. So this will give us a nearly degenerate SU4 phase space. We can just kind of think about with some small anisotropies in there. So idea is that the SU4ness of the charges that we are dealing with in this graphene system, can we do some things about it, or is there something interesting things about it? The first thing we can think about is, of course, there can be spontaneous symmetric breaking of this nearly degenerate SU4 phase space, and then this there's the SU4 spin can point in somewhere in this the SU4 space, right? For example, that the simplest example is I can just kind of polarize all the spins and leaving the pseudo spins at unpolarized, right? So that's the real kind of ferromagnets, or that we can just make the antiferromagnets. All of these things can be just utilized in a sense this manipulation of this SU4 spinners in the system, and quite early on it has been appreciated among the theorists that in fact this SU4 spins and this symmetric breaking can be quite interesting. The sample has been improved, quality of sample has been improved quite a bit in past probably 5 years, so especially. Thanks to the techniques called this boron nitride encapsulations, one can mimic this making the quantum heterostructures using the graphene and boron nitride. It's like the MB-grown samples, except that it was assembled by hand. But nevertheless, the technique has been perfected such that you can create the extremely clean interface that graphene is encapsulated between the boron nitride, and then make the device out of it. Usually mobility of the sample is now about 1 million. Turns out usually the mobility is limited by the scattering at the edge of the sample, which means the mean free path is about 10 micron, about the size of sample. But nevertheless, I think quality of sample is yet about 30 times worse than the best quality of the sample that you can see in the gallium arsenide. Now, with such a high quality sample that under the magnetic field, now you start to see the integer quantum Hall effect itself is different. For example, you see that this is a series of the internal quantum Hall effect. If you just look at all of this, basically you are seeing all the integer start to appear. In other words, the unicorn 1, 2, 3, 4, that all appears in every scale, which means basically somehow here that we break this, the SU4 degeneracy I was talking about. Of course, a strong enough magnetic field, you may expect, okay, Zeeman splitting eventually wins, that some of this lattice scale of the anisotropy also appears. But turns out, if you just look at the energy scale, that even with this kind of 30 Tesla issue of the magnetic field, or actually 12 Tesla here, that Zeeman splitting is much, much smaller than what is expected to appear as such a gap in the system. So we already see that even this simple integer quantum Hall effect, there are already interesting things that spontaneous symmetry breaking of the SU4 phase space is appearing. So maybe we can just study that what is the nature of this correlated systems by just carefully studying them. Upon that, if you just increase the magnetic field more and go to the even lower temperatures, so kind of cleaning out the sample, that also you start to see there are a lot of fractions that appear. So this is relatively old result now. There are more results actually now available. I simply didn't update this slide too much. But you start to see that at least some simple fraction, for example, here's a 1/3 sequences or appears in the between this the integer sequences. So we know that fractional quantum Hall effect can be readily available in high quality sample. Already in this stage, this is, by the way, single layer graphene under the magnetic field. You start to see that, there are some fractions appearing, but some are missing, right? And the simple arguments you can make is if you just use this particle Hall symmetry of this Landau level, especially lowest Landau level, where I expect generally spin and the valley is degenerated in the simple pictures, right? If the spontaneous symmetry breaking is breaking off with some of the sequences, say if I have the 1 Landau level, lowest Landau level, maybe it's broken off with the Zeeman splitting or valley splitting, or maybe I just break it all off in something like this. Each of the Landau level, if you just try to use particle Hall symmetries across this center of the Landau level, you can quickly rule out that pictures that describe these sequences here, they're assuming that strength of the sequence appearing in this temperature is related with the size of gap of each fractions. You start to already see that simply looking at this presence of the fractions, I can roughly tell this already start to tell us about the SU4ness of this the lowest Landau level. I just went through that a little bit quick because this is not the whole point I want to make today. So the next things that we want to look is basically, can I just look at the details of how these structures look like? And indeed, if I want to claim that there is SU4 type of the correlations appears or spontaneous symmetry breaking, what is a way that I can investigate it, right? Of course, the best way that I can interrogate this the large spin component is applying the field. Just kind of try to direct the spins in the certain directions, right? And see whether how I can just using the field integrate and break this symmetry also control the spins in that directions. The problem of the single layer at this point is we have the magnetic field. I cannot apply the outer plane magnetic field. Oh, I can do that, but that's messing around all this the filling fractions. So if I just start to apply the in-plane magnetic field, which applied only the spin sectors, that's one field I can use to integrate the real spin structures. However, for the pseudospin, which is tied with a valley or sublattice under the magnetic field, there's no good field that I can utilize to control that. So basically, I have only one field in the act on this SU4 subspace, and I wish to have the, say, pseudomagnetic field that can couple with the pseudospin. So that's not possible in the single layer. However, that's possible that for the bilayer, and that's why I just want kind of discuss about the bilayer. So graphene bilayer, usually when we just talk about the graphene bilayer that available in the nature is so-called boson stacking. If you just look at these lattice structures from the top, well, so there is carbon atoms that's sitting on the top of the other carbon atoms on the underlying layers, and one of them is not. So you can see that you can label in a different way. Nutshell that if you just again set up these Hamiltonians with a 4 motif in the unit cell, But if you just focus only on near the Fermi levels or the charge unitary point, it turns out only the two bands are relevant. And more interestingly, this two band is losing its linear dispersion relation. It becomes quadratic, such that there is a finite band mass arrives there. But nevertheless, the Hamiltonians and all of these things is rather different from just the typical the electron in the semiconductors. I will go to discuss in a moment. But the important part is there is still that inversion symmetries and time reverse symmetries that try to keep the degeneracy at this neutrality point. So without doing anything, the graphene bilayer energy structures, you still have the degeneracy right at the K point and K prime point, like the single layer. However, if I can somehow break this inversion symmetry of the systems, in other words, that if I just kind of break which one is top or bottom of this lattice, I can immediately break that degeneracy and can open up the gap. So by applying, for example, the perpendicular electric field, it has been discussed already and shown theoretically and experimentally, you can open up the gap in the spectrum. So this is kind of single particle energy gap you can controllably open through this electric field. And of course, the electric field can be polarized. These layers and up layers and down layers, they are probably the charge imbalance you can build up in the system. Now, under the magnetic field, it becomes quite interesting. Under the magnetic field, the Hamiltonians, as I just kind of write down, is that the one value versus the other one value. So it's again connected by the time reversal symmetry. If I just include the gap that I just mentioned, can open up by the electric field. Explicitly, there is a diagonal components, and the gap can be controlled. But not shared here is, say, if I just consider that there is no gap, again, there is a Landau levels that develops, very similar to the single layer. Each valley has a different the wave functions weighed in different way on the sublattice. And especially like this single layer, at the zero level of the Landau level, right at the zero energies, when there is no single particle gap opens up, the valley index is always, again, equals to the sublattice index. And interesting enough, in the low energy scale, the sublattice index is again tied with the layer index. So as I go for the degree of freedom, I can think about, all right, so I still have the real spin degree of freedom, but on the top of that, I have the valley, or same as the sublattice, or say equal to the layer, the degree of freedom I can have. And of course, as I claim that I can control the layer polarizations by electric field, perpendicular electric field. So I have basically pseudo magnetic field that couple with the pseudo spin components, right? So I have now basically two spin components that I can use for the real spin sectors and this valley spin sectors in such a way. So that's a great advantage because as an experimentalist, we have the control of this doing this one. And another interesting part is, turns out in this bilayer and zero Landau level, without again gap, it is eightfold degeneracy, and that's because of this the Hamiltonian structures. It turns out there are two oscillators are accidentally degenerate at the zero levels. So n equals 0 oscillator and n equals 1 oscillators basically somehow accidentally degenerate in the zero Landau level. Of course, this is accidental degeneracy, so any perturbation can easily break that sectors first when you just kind of come over the filling up. So again, in this regard, the bilayer graphene is an interesting system that more or less mimic again SU4 degeneracy, especially at the lowest Landau level, where that I have the kind of experimental control knobs that the controlling the two different components of the spin. Experimentally, that basically to realize this type of experiment, what you need is basically you have the top and bottom gate in the device, such that I can control the density of the system as well as electric field or displacement field, more precisely, that can couple with pseudo spin sectors, right? So here's a graphene. We just put the boron nitride top and bottoms and top and bottom gates. We can just kind of having this one under the magnetic field and under the electric field. We can interrogate the transport to understand the correlated quantum Hall. So in this chart that I'm just showing you, simply without magnetic field, applying this displacement field, charging up this top and bottom gates in the opposite the voltages, we can open up the gap and transport measurement under temperature. We can measure the gap, and gap is growing with the displacement field, and size of gap, single particle gap, can be as large as again 150 millielectric volt. So as you notice here that under the magnetic field and under the electric field, user energy scale that I'm dealing with in this the graphene case is much larger than energy scale that you see in the gallium arsenide. So the one advantage we have is we don't have to necessarily go down to extremely low temperatures to see the effects. So that's one advantage, and that also promote kind of the correlation can be strong. Now, under the magnetic field, like the single layer, we start to see the bilayer also shows the all the broken symmetry states in the high enough magnetic field. Here is a 4. Usually, single particle states only appears a 4. 9 Tesla, you have only plotted the 4 and negative 4. But as you go to the high magnetic field, you start to see that all this broken symmetry state appears. In other words, this SU4 spin start kind of including the zero lambda level, these oscillators start pointing out polarizing in interesting directions to give us all these interesting the sequences. Now, among these sequences, one of the interesting sequences is basically at the zero density. So, and the zero solar lambda levels, I would say. So you can see that there's a plateau there in this sigma xy. If you're sticking in this, the measures, the longitudinal resistance, or more precisely, if you build up the Covino device and try to measure sigma xx, it turns out sigma xx inverse, or the resistance, is keep increasing as you apply the magnetic field. So we know that in this case, there is insulating states sets up in the neutrality point, right? So which means that there should be no lambda level there. The lambda level there is splits up. Right? So, and then you can ask what actually caused the splitting at this lowest lambda levels, and then that create the gaps and make the system is insulating. So that's kind of interesting questions, right? What is the nature of those kind of the gaps that open up the neutrality? So that has been one of the really intense this subject that has been studied in this community for I think. At least 5 or 6 years and the various different methods. And then we now know the more or less answers. It turns out this the magnetic field induced insulating states at near the 0 point. It's very similar to single layer versus bilayer in terms of this nutshell. Is it greatly related with this SU4 spins that I was discussing about, right? Again, if you just kind of build up that, all right, so I have this SU4 spin, this zero lambda level, I want to kind of point that out in the certain direction and try to gap out the system. Right? There are many different ways that you can just kind of break the symmetry and gapping out. There are a few candidates, you can just kind of list it out. There are more candidates, in fact, but say if I just pictorially represent some of the scenarios is following, right? For example, that like the single particle gap, if I just put all the charge in one of the layers and empty the other layers, you can think about this is a layer polarized or kind of charge density up and down, right? And then, of course, the only way that I can just kind of do that is make the spin singlets on each of the sides. This certainly open up the gap. This is probably kind of boring gap because this is a gap that you open up with the electric field, but certainly this is one case. And presumably, if you just apply the large electric field in the vertical, the perpendicular directions, no matter what, this will be eventually preferred the situations, right? When you have the zero electric field, though, whether this is likely the ground state configuration is not clear, and probably on usually it's not likely, right? But then there are many other systems. For example, now one scenario is what if I just kind of create a spin ferromagnetism? So basically, I direct all the spin of the electrons into the one directions. And then this is basically half field lambda level at the center. So right. So the only way that I can just kind of create that is basically put the electrons in the alternating sides of the lattice and so on. Right. So there are a few of the scenarios that you can just kind of utilize there. In fact, there has been really the extensive studies happen about this phase diagram, especially now, especially considering that availability of the two magnetic field components. Say here is the Zeeman axis, and here is the layer polarization axis with the sum of this, the numbers. You can see that that how the different type of the phase of the SU4 spins can align and make the phase transitions as you just increase the field has been realized in theoretically. Of course, again, this has a very similar flavor that you can find out again in gallium arsenide. I just kind of give you a few examples, right? The valley spin is one example. Also more heavily studied is the quantum Hall bilayer. Again, symmetric and anti-symmetric states more or less form the very similar flavors of what I just described here. So it's not kind of completely new, but we have now the advantage is the knob that I can control continuously in the both of the field. So quickly go over the experiments that I can just tell you is this is conductance measurement across the this bilayer and top and bottom gates, and then I'm showing here that basically I have many knobs, right? So I have the gates control that this is more or less the gate control this displacement field, and this is basically gate control the density of the system, and this is the magnetic field axis, right? So you start to see that in the bottom, let's look at this one, zero magnetic field. The red means that the low conductance, so this is insulating, and blue is conducting. So as I said, as I go to the large the electric field, displacement field, we open up the single particle gap. So you start to see that at the zero density regions, you have the red regions, the insulating region becomes there. Now, once I turn on the magnetic field, start to develop the Landau levels, you start to see that experimentally, the central part where originally you had the conducting states turn into more red as you go to the high magnetic field, and getting to more like the insulating states, right? So I would say that this is that magnetic field induced insulating state I was referring before. So we are clearly seeing this type of things in this type of curve. Now, if you just cut, say, the zero density regimes, so which is most interesting regimes for now, just look at it, then you start to see that this is a red, red is conducting, blue is red is insulating, blue is conducting, and that was bounded by some of this whitish region, slightly more conducting. So tentatively, you can say that, well, there's a magnetic field induced insulator, electric field induced insulator. There is some sort of phase transitions as you control the displacement field, which actually makes sense, right? If you start with the magnetic field induced insulating state, which is different, which can be different natures of the layer polarizations. As I mentioned before, if I just increase the layer polarization a lot by electric field, eventually I just kind of cross one phase to the another phase by just kind of field. So this is kind of good example that how we can control. Now, I told you that there's another knob that I have that coupled with the real spins, and that knob can be only used at magnetic field in the plane, that which does not affect these orbital orders, and just only coupled with the spins. Especially think about the graphene is extremely thin. In plane magnetic field only just coupled with the spins. And then you can ask that now with this, the magnetic field induced insulators, if I just increase the in-plane magnetic field, then what is going to happen, right? So that's basically, I'm now increase the spin sectors and the real field, the field on the spin sectors. It turns out when I just increase the in-plane magnetic field, this, the magnetic field induced insulators start kind of turning to the more whitish and bluish. In other words, this is insulators that becomes more conducting, right? So I just kind of bring the insulating state in the conducting states by applying the in-plane magnetic field. In other words, that try to align the spin directions, right? So you start to see that already flavor. That sounds like indicating that this, the B field induced insulator is somehow related with the antiferromagnetic alignment of the real spin. By applying the magnetic field in plane, I try to just kind of bring this antiferromagnetic aligned real spins into the one directions. I turn it to the another phase, which is more conducting, right? So that's kind of scenario that we can just do that. You can see the bit of the details. It turns out that the insulating state turn into the metallic state as you increase the in-plane magnetic field, but quite intriguingly, that this metallic state has the conductance of very close to 4 square of H. It's not exactly quantized, it's very close. So I think probably 20 or 30% in the best case sample, right? So this strongly reminds us that, so this is a conductor, but it's not just kind of simple conductor, so we are thinking about. Maybe there's some of these edge states really carry this type of the conducting path. Indeed, what you would expect is that if you start with this, the antiferromagnet, more precise canted antiferromagnets in the magnetic field induced insulating states, turn onto the electric field, the magnetic field, and align them, and then you just close the gap. And in fact, when you close the gap, you have the conducting or counter-propagating the edge state at the edge of the sample. So more or less mimicking that quantum spin Hall effect type of the samples in the topological insulator, and that's give us this 4 square over H of the value in the system. So that's the part. So I don't think that I have enough time to go all the details. But whole point in this experiment, you can see that is basically, again, a couple of the electric field and magnetic field in plane or the outer field. We can start to control this direction of the SU4 spins. And outer plane, in fact, also control the magnetic lengths, which actually control the correlation energy of the scheme. So you can just draw all these phase diagrams and so on. But I think that's kind of interesting flavor that what we can do. Now, important part, try to make the connection with a fraction, though. I think so far that I'm just kind of talking about the integers. It's following, right? So high enough quality sample, of course, surely you start to see that, again, in the bilayer, all these fractions start to appear, right? But you can ask very similar questions. When we just have these fractions, what is the configuration of the SU4 spins you have in this system, right? So that's the interesting part. Now, of course, magnetic field is high enough, then all these fractions start to appear, and there's a sum of the hierarchical structures. I mean, Jacobi actually did a beautiful work to just kind of reveal that the internal structure of the sequences. But at the same time, we can just do the same tricks, right? We apply the electric field in this case and ask that what is going to happen, all these kind of fractions, right? And in a sense, I just discussed in the lengthy that what happens in equal 0 state, right? Not surprisingly, you can expect that all this equal 1, 2, 3, 4, all these broken symmetry states, you can just do the very similar tricks, right? Apply the electric field and magnetic field, in plane magnetic field, outer plane the electric field. You can just make the transitions from one state of the SU4 spins of the broken symmetry states to the another one, right? At the same time, you can ask that a very similar thing may happen for these fractions, right? So that's kind of part. And in the transport measurement, that appears is not a good color skills there. You can see that there is a dark, which means the RXX is 0, but if you just look at it very carefully, in some of the reaches, you start, maybe I can just bring it up, right? So this is an equal 2. There's a dark, and then there's a little bit more conducting and dark again. And so dark is insulating, and a little bit brighter, that basically there's phase transition. If you look at carefully, equal 2, for example, there's a 2 phase transitions that in some things in middle. So there are kind of interesting things comes around. What is interesting part is not only that integers, but if you look at the fractions, again, sorry for this low resolutions. So this is fractions between 1 and 2, which is a 4/3 and 5/3. If you carefully look at them, under the increasing of the electric field directions that I just mentioned, you start to see that there is a transitions appears. In this case, there's 3 transitions, right? So there are interesting the transitions appearing. If you look at very carefully, though, that this where the transition appears in terms of the displacement field, they are the same, regardless of the integer versus the fractions. If I just map it out, more or less this one is mapped, right? Whenever there is a transitions in the integer, there is a transitions appears in the fractions that nearby that integer fraction, or actually between the lower than that fraction, the filling fractions, right? And more or less, whenever that you appears that this phase transitions in the integer, associated fraction also shows this phase transition. So in a sense, it's not surprising because this composite fermion is inherited some of the structures of this the integer quantum or the states. So the phase transition appears a very similar case. It's not surprising, but this is the interesting part. There are some cases, though, that there's only the transition appears in the fractions, but not in the integer. So it's not always faithfully follow. But interesting part is whenever there is a coincidence, that displacement field that make this type of transition is always equal. Right. And you can just come up with the why there's number of the phase transition appears by just considering this mean field type of the considerations and just propose some of this the SU4 spin direction into the system. So that's can be done. Right. So another thing, of course, is at the same time, like the electric field, we can also apply the in-plane magnetic field. Now also kind of attack the spin sectors, and you start to see that. That of course this in-plane magnetic field start kind of move around the transition point of this displacement field transition point, and basically in principle you can construct this kind of rather complicated phase diagrams, electric field and magnetic field and the displacement. So energy here, that electric field and magnetic field. You can just draw that. Okay, so here's a ferromagnets turn into the layer polarizations, antiferromagnetic layer polarization. All of this phase space can be constructed not only the integers, but also the fractions. I have probably 5 minutes. No time? Okay, time is up. So then I don't probably have the time to discuss about the outlook, but I can just mention quickly, just in 30 seconds. First one is, of course, the experimental start allows us to also doing the not only bilayer, but also the really quantum bilayer, and then you can look at the drag signals. And again, compared with gallium arsenide, we have a bit of more controllability. That contact on each layers and controlling the density of each layer in the wider range is possible, right? So this start allows us not only just confined to look at this quantum drag in the lowest lambda levels, half-year lowest lambda level, but already experimental start shows that there's a lot of different type of drag of signals that in the different lambda levels. And of course, you can just kind of expand this one, what happens in the fractional quantum, what kind of the drag effects you will get. I think that's kind of interesting part. Yeah, don't have the time to kind of discuss other things, but yeah, let me just bring it up. My summary, and thank you for your attention. Yeah.
You went by a bit fast. There's a state that you show that with the pseudo space where you have edges. Did you say there's a counter-propagating?
Right.
So can you show that picture?
Yes.
The one that you say is similar to the topological.
Yes, that's right. So that's of course in this case the apparent similarity is there because it's counter-propagating edge states, something like this. But of course here that we use magnetic field to explicitly break this counter-propagating.
Arrows
right.
are valley index or.
So that's a real spin index.
The real spin.
Right, so that the up and down arrow is a real spin index. And this is at the valley gap that we have, right? Sorry. So this is a spin gap we have, spin up and down, right? And then this is the valley gap that opens up, right?
So why did you have counter-propagating current?
In these schemes, basically, if you look at the how the edge state is created, it's basically group velocity is opposite, right? And then it tied with the spin direction, spin polarizations,
so this is
right?
the one that you can put in silver conductor.
In principle, that you can do that. In fact, this is one way that you can also realize Majorana. But thanks for asking because it's related with your interest later on. Is the more interesting the part is following that you don't have to in fact just to rely. Oh, that's one of the scenario. But the other one is you just kind of couple with the superconductors with the quantum edge state, which is now possible, right? And if you think about this superconductor is really, really narrow, something the range of the superconducting coherence length. If there's edge states kind of circulating around, you can couple these two edge states with the superconducting orders, and then you can create this Majorana. And theoretical predictions out there that are made at Alessia, Stengels, and so on. If you expand that into the fractional quantum regimes, then what you expect is not the Majorana, but generalized Majorana, what they call the parafermions and so on. So that's some of the proposals out there. Yeah.
I noticed you're working in the range 0.3 to 2 Kelvin or something in that range. Are there material issues that keep you from going colder?
No. I think.
Would you expect to see more fine structure?
Sure. Yeah.
States?
Eventually, right? So the reason that we are working on 2 and 3 Kelvin a lot of time is not because we don't have the fridges. It's because that's already good enough to see what we want to see. Right now there's still remaining disorders, give a disorder energy scale, which is usually about Kelvinish, right? So below that, going to below the Kelvin does not gain you too much in most of the time. That's why we don't necessarily need to go there. But certainly if you clear out this system more, and then we just kind of get to this disorder energy scale much smaller, and then like the Gabo, that getting to the lower temperature will get the most structures for sure. Yeah. Yeah.
So in this SU4 picture, the valley and the spin is coupled.
Sometimes I think so for ferromagnetic. Okay, so in a sense it's coupled, right? Okay, if it is coherent states, yes, yeah.
So can you use then magnetic field to control the valley, or vice versa? Say use I don't know, strain or whatever pseudo magnetic field to control the spin.
Yes and no, depends on what is this state, the ground states you are just kind of dealing with, right? So if you just kind of break the spin sectors or align the spin sector, that naturally affect the valence sector in some states, but not necessarily all these the configurations. Sometimes they're kind of completely orthogonal and independent. Then you can just separate things, right?
So you talked about drag.
Yeah.
Have you looked for like excitonic superposition?
Not yet in a sense, but we just kind of based on what Eisenstein already did beautifully, seeing this, we are seeing the really kind of well quantized drag. And if we just kind of believe that, like the Eisenstein's experiments, this quantized drag is in the end the signatures of these exotonic condensations, then I would say that this is kind of very first step that we can claim the exotonic condensations, right?
At what filling factor are you seeing?
It's in this particular one that we are showing is half and half, but we are also seeing now half and 2.5, and also the other electron whole side we are seeing that basically 3 halves and 3 halves, negative 3 halves and 3 halves. So apparently there are many of the drags, not only the same lambda levels, but different fillings of the half here, and not all of the half here, but some of them. So there must be some rules that we try to figure it out now. Yeah.
Okay, if there are no other questions, let's thank Philip.
Thank you.